what we're going to kick things off with today is a look at a comparator circuit where we have included some noise on our input. And I cannot tell you why, but for the life of me, I never remember to save this thing year to year. So I was hurriedly trying to make it out in my office. But effectively what I have is a simple system. So this voltage source over here on the left is my power supply. I have my reference voltage, and then I have that sinusoid. And on top of that, I've superimposed some white noise. And if you give me just a moment, I'll put together the OpAmp circuit and we'll take a look at what the output does.
What word do you type for that out?
UNI. All right, so let's see, label network, there we go. ECC plus goes down here. All right, so when I run this simulation and I look at my output signal, why is it doing? Oh, I know why. I never labeled this guy down here as VCC minus. That should fix it. There we go. Yeah. So right now, let me move this thing out of your way. Everything seems hunky-dory. And the reason is because I'm only applying the sinusoidal input that's a pure sine wave, right? But in practice, it's very likely that we are going to have some noise on our supplies. Now, this is a little bit exaggerated from the amount that I put on here, but we can clearly see that our green curve, the input, is that 2.5 volt amplitude sine wave on top of a 2.5 volt DC offset. And then on top of that, I've added some noise, which is why it kind of squiggles all over the place, right? So if I change this input signal from Vin to the voltage Vin plus N, which is what I've labeled my noise superimposed on top of my input signal, and I run this simulation, it's going to take it a minute.
What is a white actually doing? Just like giving like error bars?
It's generating white noise. So white noise means noise that doesn't, or white noise is noise that has a constant power spectral density over the entire frequency band, right? So all the way from roughly 0 hertz up to terahertz levels of frequency, white noise is effectively constant. So it means that it doesn't matter what frequency our circuit is operating at, it's just going to add a little bit of variation, some above, some below. It has a Gaussian distribution, so you're not going to see like a spike of 1,000 volts or anything like that. It's just going to be in a little bitty range around the input signal. Pardon?
Kind of like a Perlin noise.
I don't know what a Perlin noise is. So this is like Brownian motion in so like effectively just a little bit of thermal jiggle, right? it should be wrapping up here in just a minute. Oop. All right, so it's pretty much finished now. So this looks significantly different than the output without noise, right? And the reason why it's different is because as we have noise very close to our reference value, because of the high gain of our OpAmp, the high open loop gain of our OpAmp, a small variation above the reference causes it to swing high. And then if the noise causes it to dip below V reference, even just a little bit, causes that output to swing back low. So you're seeing wild oscillations of the output when there's noise close to our reference value, okay? Which is less than ideal behavior, okay? So we're going to fix this by applying positive feedback and creating what's called a Schmitt trigger circuit, okay? So that's where we're really going to start off today. So positive feedback circuits. So if we take an open loop amplifier circuit, like so, here's our output voltage. And then we apply a conduction path where I'm just using a generic circuit, a generic circuit element here between the non-inverting input terminal and the output terminal. And then let's just say, for the sake of argument here, let's call this V1. And let's call this guy V2. We have a closed loop system, okay? The location of this closed loop, meaning that it's connecting the non-inverting input to the output, means that we have positive feedback, okay? So a positive feedback system is an unstable system, but it's more controlled than an open loop system. So let's say, how many of you guys have ever been at an assembly or anything like that and heard feedback over the speakers? Okay, probably most of us at this point, all right? So that's a positive feedback system, okay? You have somebody talking into a microphone. That microphone converts the pressure wave that is their speech into an electrical signal, which is then amplified and created into a secondary pressure wave by the speakers. Well, if the microphone picks up any of the output of the speakers, it amplifies that again, and it cyclically goes over and over and over and pushes the output of the system to an extreme value. For an OpAmp circuit like this, the extreme value is going to be VCC plus or VCC minus, okay? So we're still going to see that our output values are always only going to be effectively VCC plus and VCC minus, but we have a little bit more control over what's happening because there is some feedback going on that we can establish some control with. So our first circuit is going to be the non-inverting Schmitt trigger. And it's going to look something like this. And I am leaving off the power supply voltages with the understanding that we know it's an op amp and so it needs to have power. So for the non-inverting Schmitt trigger circuit, we apply our reference voltage to our inverting input terminal. And then we tie our non-inverting input terminal to our output terminal with a resistor, which I am just going to call R2. And also going to put in our little biasing network here a resistor R1. And we apply our input signal at the other leg of resistor R1. Okay. So what we're going to do is we're going to apply the practical op-amp model here with some very specific assumptions to kind of figure out how this guy behaves, to develop some sort of input-output relationship for this thing. All right. So let's start by drawing my basic practical op-amp model. I have my resistance Rn. This is my voltage at the non-inverting input terminal. This is my voltage present at my inverting input terminal. The potential difference between these guys is my differential voltage VD. There's my output resistance. Here's my output voltage V out. Okay, so that's my practical op-amp model. Now I need to connect things, right? So between my inverting input terminal and ground, I have some voltage V reference. Between my non-inverting input terminal and V out, I have a resistor R2. And between my non-inverting input terminal and ground, I have a resistor R1 in series with my voltage source Vin, and this node down here is ground.
You just assume that's connected to the positive terminal will be out.
So this V out terminal is the output voltage measured with respect to ground. So it has to be connected to the positive polarity terminal because the output is measured with respect to ground. If it was connected to the negative polarity terminal, V out would always be 0. All right, so did how I redrew this circuit Is that okay? Anybody got any questions, comments, or concerns? Or all right. So the assumptions that we are going to make and these just make the analysis much easier, is that our input resistance Rn is much, much greater than R1 and R2. And our output resistance is much less than R1 and R2. This is second assumption here that R out is significantly less than R1 and R2. Effectively, it's just forcing V out to be AVOL times VD or VCC plus in some cases and VCC minus in the other cases. So this is what it's fixing our output swing to go from VCC plus to VCC minus. All right. The assumption that Rn is much greater than R1 and R2 means this current has to be 0 amps or very, very close to 0 amps, right? No current. So if we say that this input voltage is going to cause some current to flow through resistor R1, practically none of it is going to branch off and flow through the input resistance. All of it's going to flow around that loop. All right. So what that means is that if no current is flowing through this resistor, VD, our voltage, is approximately 0, which means V plus is essentially V reference. Okay. So I know this is a little wonky here because I just said that V out is going to swing between VCC plus and VCC minus, where V out is equal to AVOL times VD. And I'm now saying that VD is approximately 0. That just means that AVOL is really, really large. So it's still amplifying some very, very small signal on the order of a couple of millivolts or something like that, maybe even microvolts, but it's providing enough amplification to push this thing to saturation and negative saturation, okay? So it seems like a little bit of a conundrum here, but that's why I'm not specifically saying our differential voltage is 0. Similarly, that current really isn't 0 amps. It's just very close to 0 amps. It's much smaller than the currents that we would see flowing through resistors R1 and R2. So what we can do is we can write a Kirchhoff's current law equation at our non-inverting input, okay? So we're going to have this current plus this current, add them together and set them equal to 0, where again, we're neglecting the effect of the current that's flowing through that input resistance Rn. And since this current flowing to the left has something to do with V in, this current flowing to the right has something to do with V out, it's going to be pretty straightforward that we're going to get an input-output relationship out of this guy, right? So let's see. So we're going to have Vref minus Vn divided by R1 plus Vref minus V out divided by R2 is equal to 0. And so what I'm going to do now is I'm going to put all my V reference terms on one side of the equal sign and all my not V reference terms on the other side of the equal sign. And we will find that we have the nodal voltage right here is V out. So V out, excuse me, V plus minus V out over R2. Excuse me. So we'll have Vref times 1 over R1 plus 1 over R2 is equal to Vn over R1 plus V out over R2. I can make this sum of the reciprocals. So the easiest way to think about this without doing algebra, so this is just the inverse of R1 in parallel with R2, right? Because R1 in parallel with R2 would be 1 over this whole thing. So R1 in parallel with R2 is R1, R2 divided by R1 plus R2. The inverse of that is just R1 plus R2 over R1 times R2. So this is going to be Vref R1 plus R2 divided by R1 times R2 is equal to Vn over R1 plus V out over R2. Oops, I went too far. And now I can just isolate Vref. So this is going to be R2 divided by R1 plus R2 times Vn plus R1 over R1 plus R2 times V out. I'm going to put a box around this guy. So this is our characteristic equation for this circuit. This is telling us how it behaves. And it looks a little bit different than what we've seen previously because it's telling us how our reference voltage relates to both the input and the output. The reason why we get such an interesting relationship here is because we know that the output can really only have two states. It's either going to be VCC plus or VCC minus. So what this tells us is effectively, we're going to solve for the input value that causes our output to either swing high from a low state or the input value that causes the output to swing low from a high state. These are what are called our upper trigger limits and our lower trigger limits. Okay. So let me define these real quick over here. UTL is the value of Vn that causes V out to change from VCC minus to VCC plus. So the upper trigger limit makes the output switch from low to high. And then the lower trigger limit is the value of Vn that causes V out to change from VCC plus to VCC minus. Cheston.
I noticed that this looks like voltage division, so how come you wouldn't use V out to do R2? That you wouldn't flip V in and V out? Because V in, you know what I'm saying?
We're using we're figuring out V in because we know how V out is going to behave. It's either going to be VCC plus or VCC minus. Now we do have ratios of resistances here that does look voltage division-y-ish, but that's not really what we're doing here, okay? So if, Brandon. Oh, so what I was gonna say, like if we simulated a circuit here, so let's go to our simulation, all right? Let me get my keyboard. We're going to throw some resistor values on this. So I need to apply some form of positive feedback. And then, so let's put a resistor there. So I think this is where we said R1 lived, and up here will be R2, right? For the sake of argument, let's make this guy a 5 kilo ohm resistor. Let's make this guy a 1 kilo ohm resistor. And we are going to apply our voltage Vn, excuse me, Vn plus N. Actually, let's just do Vn for now, just because I don't want the simulation to take a long time to do it. And let's run things here. And I'm going to delete. So I want to look just at Vn and V out, and I'm going to play with these guys a little bit. So let's make this 5.5. Let's make this negative 0.5. So we can really see what's going on here. Okay, Alexis.
Shouldn't there be C minus and plus be swap, or are they supposed to be?
No, they're supposed to be like this. So for the universal op-amp model, for whatever reason, the positive power supply voltage is on the inverting terminal side. So there's a little bit of plus sign here that tells me that's where VCC plus goes. And there's a little bitty minus sign here that tells me where VCC minus goes. I don't know why the model is set up that way, but it is. So those are technically correct, even though it looks wrong. In fact, if you put a lower potential voltage here than a higher potential voltage here, the op-amp won't turn on in the model. So it looks janky, but it's correct. All right. So what we can see here is that when our output exceeds something in the ballpark of 4 volts, or excuse me, when our input exceeds something in the ballpark of 4 volts, our output swings high. But it doesn't go low when it gets less than that 4 volts. It actually goes low when it's less than 3. So we have latching going on. Okay, the output is staying high until some secondary condition is met. And then similarly, the output stays low until Vn gets larger than this upper trigger limit. And it stays high until Vn gets less than that lower trigger limit, right? So that's what this mathematical equation is telling us how to solve for, is the upper trigger limit and the lower trigger limit. So we need to solve for Vn for a known value of V reference for a particular value of V out, because we know that it's going to change from one state to the next state, okay? So these look voltage division E, but we're not doing voltage division. That's just how the math happened to work because of the layout of the circuit. All right, so with these definitions that we have here, let's analyze our circuit in particular, okay? So we had Vref was equal to 3.3 volts, right? That's what our simulation had. We can double check that real quick. V reference is 3.3 volts. R2 is 5K, R1 is 1K. All right. So if we want to find the upper trigger limit, our equation is going to look like V reference, which is 3.3 volts, is equal to R2, which is 5K, divided by R1, which is 1K, plus R2, which is 5K, times Vn, which is what we're trying to solve for, plus R1, which is 1 kilo ohm, divided by 1 kilo ohm plus 5 kilo ohms times V out. So it's very important that we put the right value of V out here, okay? The upper trigger limit is the voltage that makes the output swing from VCC minus to VCC plus. So we want to put the VCC minus value in for V out whenever we're calculating the upper trigger limit, which in this case is simply 0 volts. And so our upper trigger limit occurs when Vn is equal to 3.3 volts times 6/5. Or 3.96 volts. So if we look at our figure, that seems to make a lot of sense, right? This isn't quite 4, but it's pretty dang close. So that seems like a reasonable estimation of our upper trigger limit. We can calculate our lower trigger limit. By doing effectively the same thing. So we'll have 3.3 volts is equal to 5 kilo ohms over 1 kilo ohm plus 5 kilo ohms times Vn, which is our variable of interest, plus 1 kilo ohm divided by 1 kilo ohm plus 5 kilo ohms. And now we put in VCC plus for our output because we want to know what forces the output to change from VCC plus down to VCC minus. And so this is going to look like 3.3 volts minus 1/6 of 5 volts is equal to 5/6 of Vn. So that means we're going to have 6/5 of 3.3 volts let's see, minus, oh my gosh, so let's see, 6 times 1/6 is going to be 1/5, right? Sixes cancel each other out, so minus 1/5 of 5 volts. Or 2.96 volts, which is effectively what we see. Something really close to 3 volts is when the output goes low, right? So our simple mathematical model has predicted the upper trigger limit and lower trigger limit of our Schmitt trigger. Now, just for the sake of argument, let's change this input signal from Vin to Vin plus N. Our noisy voltage I'm going to rerun the simulation because it's still using just the old value of the output.
Why don't we account for the gain? Wouldn't that change the slope? Wouldn't change the intercept?
So sorry, I was about to. So the slope is just telling us how quickly we transition from VCC minus to VCC plus. So we can play with the gain in here and see what happens, right? So right now, we're just illustrating the point that we get the nice, even output without all the crazy fluctuations and all that kind of stuff. So this handled some of the noise for us, but we don't have a simple single comparison anymore, right? We no longer have when Vn is greater than V reference, it's high. When Vn is less than V reference, it's low. Now we have these latching mechanisms kind of built in, which is absolutely a useful thing. So let's play around and see what happens if we drop our gain, right? So let's move the spice level from 2 to 3. And let's drop our gain. Right now it is 1,000,000. So let's drop it to 0.01. So that'd be 10,000, right? So that's a pretty appreciable decrease in the gain. What is it telling me? Unknown subcircuit. All right, well, let's just see what it does. Doesn't seem to have any real change here. 0.01, okay. Let me see what happens if I change this to just VN. I think it might not like the fact that I have a plus sign in one of my labels. Nope, still doing it. I'm not sure what exactly is going on in here or which of the subcircuits it's saying that it isn't particularly caring for, but it's looking like not a whole heck of a lot is changing here. Let me 1,000. Still doing the same thing. The only thing I'm changing is the gain, so it's just one of the nodes that it doesn't like the way I'm referencing it. But it's still not having any real change on the output. We do, for whatever reason, see a little Gibbs phenomenon dip up here, but that slope is still high enough to cause it to swing from VCC minus to VCC plus very, very quickly. So because we have a positive feedback, and it would be a pain in the ass for us to actually go through and really calculate what the linear range of this guy is with all the feedback stuff in there, with our limited amount of knowledge of how feedback circuits behave. But the linear range of this positive feedback circuit is actually going to be a little bit smaller than the linear range of an open loop circuit because of the way that the feedback is applied. Okay. So we are still, even though the gain here, the open loop gain is down to 1,000. So it's 1,000 times smaller than what we started with. We see no observable difference in the output whatsoever. Yes,
Do you
Ian.
know why the input noise seems a little bit different around that 3.3 volt?
Because of the way that I've entered it in. So this should be random, but it isn't. Like in a real random number generator, every time I ran this simulation, it would be different. I chose this value very specifically to give me a significant bit of noise around the reference value that we've been doing, right? So if I changed this, I believe it'll make it blah, blah, blah. I can't remember whether it looks significantly different or not, but effectively you can play with the parameters of the white noise generator and it'll give it different peaks in different places. It's not truly random where it would be different every time, but
How do you know how large? Like 3 times 10 to the 6, is that just arbitrarily?
just playing around with it to get it to mess with the specific points that I wanted for this particular example, right? So in a true white noise system, you're just as likely to be slightly above your value as you are slightly below the value. And the standard deviation is going to be that you're only going to, what is it? You're going to be within 1 standard deviation on either side. 2/3 of the time, you're going to be within 2 standard deviations. Like 90% of the time, you're going to be within 3 standard deviations on either side, like 97, 6 sigma or whatever, 97% of the time. But for whatever reason, LT spice gives me a lot of noise right at around the 3.3 volts reference that we've been dealing with. And so I can play with it, like I can divide it by a factor of 10 or something and it would make it smaller. I don't know. You just play with the different parameters and it just gives you weird looking noise. That was the whole point of it, is to make it not be a clean sine wave anymore. All right, so we have gone through a reasonable amount of detail to figure out the behavior of a non-inverting Schmitt trigger. Okay. So the next thing that we're going to look at is an inverting Schmitt trigger. All right, and I'm going to do no analysis whatsoever. So the difference between a non-inverting Schmitt trigger and an inverting Schmitt trigger is that you replace where V reference and Vn are applied. You literally just swap those 2 voltages. Okay. Just like the difference between an inverting comparator and a non-inverting comparator was just swapping Vn and V reference. So all I'm going to do in this equation is swap Vn and V reference, and it gives me my equation that governs how an inverting Schmitt trigger works, because the circuit analysis is exactly the same. It's just those 2 voltages are swapped. Does that seem like a reasonable approach to not doing math? All right. So for our inverting Schmitt trigger, we'll have our same basic circuit. We'll have our feedback resistor R2 that connects the non-inverting input to the output. We'll have our resistor R1 out here. This is where the ref will be applied. The N will be applied directly to the inverting input terminal. And our relationship now is Vn is equal to R2 over R1 plus R2 times Vref plus R1 divided by R1 plus R2 times V out. We don't even have to do any work to solve for our upper trigger limit and lower trigger limits now, because we have an expression that relates Vn only to the known quantity. So no algebra or anything like that, right? Definition for the upper trigger limit and the lower trigger limit do not change. The upper trigger limit is always the input voltage that causes the output to go from VCC minus to VCC plus. The lower trigger limit is still the input voltage that causes the output to go from VCC plus to VCC minus, okay? So no analysis needed whatsoever for the inverting Schmitt trigger because it's the same circuit with just two voltages swapped. All right, so does anyone have any questions regarding this Schmitt trigger circuits? Obviously, if we needed to, we could apply our reference voltage using some sort of bias resistor network, like voltage divider network, like we did the other day as well. Not going to beat that horse to death again, because I think the methodology there is fairly straightforward. So the last circuit that I want to talk about today is something entirely different. We are going to talk about an OpAmp multi-vibrator circuit, or OpAmp astable multi-vibrator. Okay. This circuit technically contains both positive feedback and negative feedback, but if a circuit contains positive feedback ever, it's a positive feedback circuit. That's what's going to govern what happens, okay? So start with our op-amp. I am choosing to draw this one with the inverting input terminal on top, the non-inverting input terminal on bottom. So this is different than the others. VD is still the exact same thing, all that kind of good stuff. It's just easier to draw with the plus sign on bottom there. This is going to be a resistor R1. And so that is our feedback, our positive feedback resistance. We are also going to have a negative feedback resistor that I'm just going to call R. Here is R2. Here we have a capacitor, C. And this node will be ground, and this guy can be powered VCC plus, VCC minus. And here is our output node. What's the first thing? I've completed drawing this circuit. So what's the first interesting thing that you notice about this guy? Sunny. That doesn't particularly matter. Capacitor, okay, so that's something we haven't dealt with in any of these OpAmp circuits yet. It is interesting, and it is going to tell us how this guy behaves, because since we have a capacitor and some resistors here, we are going to see some simple RC charging and discharging and all that kind of good stuff. What's something else that's pretty interesting about this guy? Yes, sir. The lack of, so let's say specifically the lack of an input voltage, period, right? So we have a power supply voltage here and a power supply voltage here. We have an output, but there is no input voltage to this guy. This circuit is used to generate a square wave signal. Okay. The frequency at which the square wave is generated is dependent on these component values. So this is an astable circuit, meaning if you hook it up, perturbations in the energy stored in the capacitor cause the output to start swinging. And the amplitude of those swings gets larger and larger and larger until it starts swinging from VCC plus to VCC minus, and the frequency is set by these components. So this is how you make a square wave without putting in any frequency dependent input signal at all. Okay. So we want to talk our way through how it works. Let's call this voltage here, the voltage drop across the capacitor with respect to ground, VC. And let's call the voltage here present at the non-inverting input terminal V reference, because these are effectively going to tell us how it switches and when it switches and all that kind of good stuff. All right. So let's assume that this system starts with a condition of VC is equal to 0, meaning our capacitor is fully discharged and V out starts at VCC plus. Okay. So if V out starts at VCC plus, this is a positive voltage. This voltage here is 0. So we should expect to see some current flowing through this resistor R. Right? That current flowing through resistor R is going to effectively charge that capacitor. Now on the other side, we have a simple voltage divider circuit where Vref is just going to be equal to V out times R2 over R1 plus R2, right? So this guy is going to start at no voltage, but begin increasing. This guy is set to some fraction of VCC plus. Now, when the capacitor charges enough, this is going to be at a higher potential than this node, and then it's going to start the other half cycle. And it's just going to cycle back and forth, charging and discharging, charging and discharging. And so we should see something like this. Okay. So if this is time, let's do purple for VC. So it's going to charge, discharge, charge, discharge, charge, discharge. And at the same time, our reference voltage is, so this will be Vref, this will be VC. So when the capacitor voltage meets the reference voltage, the output swaps. The capacitor starts to discharge, swaps again, starts to charge, swaps again, starts a discharge, et cetera, et cetera, et cetera. The output signal is just oscillating between VCC plus and VCC minus. So this blue curve is V out. This will be VCC plus. This will be VCC minus, and the period of oscillations, T, is given by T is equal to 2 times R times C. So that's just twice the time constant multiplied by the natural logarithm of 1 plus beta over 1 minus beta, where beta is equal to R2 divided by R1 plus R2. So this tells us how quickly the system oscillates. It's oscillating from VCC plus to VCC minus, and we can tune any of these things really to change the frequency, right? So we can change the size of the capacitor, we can change the size of the resistor R to get big changes in the frequency, since frequency is just 1 over capital T, or we could make changes to R1 and R2 to get smaller changes in the output, right? So we can make a clock circuit using this without having to need any crystal oscillators or anything. All right, that's enough out of me for today. I'll have your third homework assignment up either later today or very early tomorrow morning. Since today's class is on a Wednesday, it'll be due next Wednesday. Everybody doing okay with the homeworks and all that kind of stuff? I think your first one is due this upcoming Friday at midnight. I've seen that several of you have already turned it in, and a few of you have come to ask questions for homework too. So I'm very pleased that you're actually, doing the work in a timely fashion and all that kind of jazz. If you have questions about anything, we still have 15 minutes left of class, so you're free to ask them. There's also the Eta Kappa Nu tutoring sessions still happen down the hall here on Monday and Wednesday evenings from 4:30 to 5:30 p.m. If anybody has any questions, I want to come ask that. All righty, see you guys on Friday.